We're talking about random processes, and we're going to define the power spectral density of a random process. It's defined as the Fourier transform of the autocorrelation function. The concept only applies if the process is at least wide-set stationary. Here's what a Fourier transform is for our purposes. And by the way, Fourier transforms aren't defined the same everywhere. Mathematicians define it one way, engineers define it another. Engineers use this minus sign in the exponent. I believe mathematicians don't. And some textbooks use omega in radians per second, and some use F for frequency in hertz. So we're going to do it like engineers. We'll either do it this way or that way, in radians per second or hertz. And you can recover if you have the power spectral density, and you could get the autocorrelation function by taking the inverse Fourier transform. And here's what that looks like for omega in terms of radians per second, or if you do it in hertz, you don't have to divide by the 2 pi. For any physically realizable process, power spectral density has to be real. It's a symmetric function of frequency. It's a mirror image on the right and left side, and it never goes negative. And by the way, if you look at the mean square, remember the mean square of a stationary process with the autocorrelation function with an argument of 0. That is, I put a 0, here. If I put a 0 for tau here, I have a 0 here, this just becomes a 1. And so it's just the area under the power spectral density. If you integrate the power spectral density, the area under the curve, that's the mean square value. Well, if it's defined in terms of hertz. If it's defined in terms of radians per second, you got to divide by 2 pi. So if you find yourself confused a little bit by the factor of 2 pi, it's understandable. Intuitively, if you have a narrow autocorrelation function, you have a wide frequency spectrum. Conversely, if you have a wide autocorrelation function, you have a narrow frequency spectrum. Remember, if it's a narrow autocorrelation function, you expect it to change more rapidly, to be a jittier time plot. Kind of a spoiler alert, if you go to the extreme, where this guy becomes a Dirac delta function and this guy just becomes a constant, that would be white noise, pure jitteriness, no smoothness whatsoever. We'll get to white noise in later videos. Let's take this guy. Let's say this is the autocorrelation function of some random process. Is it physically realizable? Well, let's look at its power spectral density, which means just take the Fourier transform of this guy. If you have a Fourier transform table, this is a pulse in the time domain, which is a sink in the frequency domain. The sink goes negative sometimes. Can't be true for a physically realizable process. So this is not a physically realizable process. Power spectral density goes negative. Here's a little example. Somebody gives us power spectral density, and we're going to be asked for and find the autocorrelation function. It has a Dirac spike at the origin. Is a pair of Dirac spikes, and if it's physically realizable, these guys have to be symmetric. In this case, they are. So there's one on the left with a height of a half, and on the right with a height of a half. Then you've got this continuous part. So the autocorrelation function is going to be the same linear combination of these guys. We're going to need certain entries from a Fourier table. Let's see, this guy kind of looks like this in a Fourier table, which in the time domain is this exponential. The Dirac delta function at the origin translates to a constant in time. And this pair of Dirac delta functions is going to correspond to a cosine time. This is a Fourier table where we have t for time. RT is going to be a tau for the time difference of the autocorrelation. I'm not going to go through all the calculations here, but here's what's in the table. And we have to take what's actually given to us, use the table to find out what all the scales and what all the constants are. So the continuous part, here's what's in the table. It will match us, our case, if this little a is a 1 and the big A is a 1. And the autocorrelation function corresponding to that factor, e to the minus absolute value of tau. Impulse at 0, if you match coefficients, I need to multiply by 1 over 2 pi. Here's the autocorrelation function for that part. And the impulse pair, you have to divide by 1 over 2 pi again to make it come out right. So here's the autocorrelation function to that element. They all get added up, and here is my overall autocorrelation function. It's this decaying exponential, but then it has periodic components. It has this constant component, and it has this cosine, which is a periodic component. And that's what these Dirac delta functions tell you. You're going to have periodic components. This 1 at the 0 means you're going to have a constant component. These guys mean you're going to have cosines. This is kind of a biggie. Power spectral density has no Dirac spike at the origin. The mean of the process is 0. So now we have two ways to know if the mean of the process is 0. If this limit was 0, limit is tau goes to infinity of the autocorrelation function. If that was 0, then the mean of the process was 0. And if there's no Dirac delta spike at 0 in the power spectral density, the mean is 0. So the example we just did, we had this spike at 0, so we couldn't say that it had a 0 mean. Like it's got this constant thing, so it's not going to have a 0 mean. And in fact, this limit doesn't even exist as tau goes to 0 because of this cosine of tau. It oscillates forever. There's going to be some component that oscillates forever. Remember, this implication only goes one way. If this limit equals 0, then the mean is 0. But if the mean is 0, it does not necessarily imply that this limit is 0. But if it has no periodic components, meaning no Dirac spikes in the power spectral density, then it does go the other way. If the mean is 0, then this limit will exist and be 0. But even then, let's see. What if it has a mean of not 0? There's no Dirac spikes, then this limit will be the square of the mean. Okay, I think that's enough for this video. So we introduced power spectral density. Found another way to see if the mean is